going to start here with parallel lines and their angles. Last time we used our angles to prove, or rather we used our lines to prove our angles to be congruent, and today we're going to use our angles to prove our lines parallel. So if two lines are cut by a transversal so that the corresponding angles are congruent, then the lines are parallel. Our shorthand will be if corresponding angles congruent, then parallel. If two lines are cut by a transversal so that alternate interior angles are congruent, then lines parallel. So if alternate interior angles congruent, then parallel. If two lines are cut by a transversal so that alternate exterior angles are congruent, then lines are parallel. So if alternate exterior angles congruent, then lines parallel. And if two lines are cut by a transversal so that same side interior angles are supplementary, then lines parallel. So if same side interior angles are supplementary, then lines parallel. All right, these are our converses, and we'll start using those in proofs here in just a minute. Transitive property of parallel lines. If two lines are parallel to the same line, then they are parallel to each other. So here is a proof for us. We are given that our lines A and B are parallel. So I'm going to go ahead and come over here and give those a marking. And I want to prove that angle 5 is congruent to angle 4. Now, we don't necessarily have to prove this because 5 and 4 are already alternate exterior angles. And if lines are parallel, alternate exterior angles are congruent, so just keep that in mind. But let's go ahead and follow what the proof is asking of us. So it's starting out with 5 and 7. Well, if I look at 5 and 7, I see that those two are corresponding angles. So if lines parallel, those corresponding angles will be congruent to each other. And 4 is congruent to 7. Those are vertical angles. And our postulate tells us that all vertical angles are congruent. And then this is setting up for us. If 5 is 7 and 4 is 7, then 5 and 4 are also congruent. And that is our transitive property of congruence. All right, so in this case, we want to prove that our lines are parallel. So one thing I want you to take certain mental note of is that if I need to prove my lines parallel, I cannot use a reason with if parallel in it. Okay? If we don't know that our lines are parallel, we cannot use if parallel until after we know something to be parallel. So we're going to start out here. We are given that 1 and 4 are supplementary. So I'm just going to, I guess, maybe highlight those. 1 and 4 are supplementary. And I want to work my way to prove that my lines are parallel. As it stands right now, 1 and 4 do not have a direct relationship to one another. It doesn't work that way. So we're going to have to find another way around it. Let's follow the proof and see what it has to say. So the measure of angle 1 plus the measure of angle 4 is equal to 180. Well, this is just our definition of supplementary. I'm just changing it so that I can work some math with that. So definition of supplementary angles. If they are supplementary, then they add to be 180. The measure of angle 3 plus the measure of angle 4 is equal to 180. If I look at 3 and 4, I see that those two are a linear pair. So this is our linear pair postulate. You could also put if linear pair, then supplementary. So linear pair postulate. Because both of those are equal to 180 degrees, I can set them equal to one another. So this could be our transitive property of equality, or it could also be substitution. The measure of angle 4 equals the measure of angle 4. That is our reflexive property of equality. And we are using that to then subtract out the 4's so that I have 1 and 3 remaining. So subtraction. And since our theorems revolve around congruence, I'm just changing how this appears. So this could be our definition of congruent angles. And now go back up and look at the picture. What we've just done is proven 1 and 3 congruent. So if I move back up here, I'm going to erase some of this stuff. If I prove that 1 and 3 are congruent, those are corresponding angles, and what I know from my converse is that if corresponding angles are congruent, then my lines are parallel. So if corresponding angles congruent, then lines are parallel. Now, I want to take a little sidebar here, and I want to work this again in the same exact way, but using the congruent supplements theorem. So we can start out with our given. Angle 1 is supplementary to angle 4. But instead of changing all the words around, let's just keep with that track. So instead of saying that 3 plus 4 equals 180, let's say angle 3 is supplementary to angle 4 because they are a linear pair. And if 1 is supplementary to 4 and 3 is supplementary to 4, then I automatically know that angle 1 is congruent to angle 3 because that is our congruent supplements theorem. And that right there is enough to prove that A is parallel to B, because if corresponding angles are congruent, then my lines are parallel. So this took us 1, 2, 3, 4 full steps, whereas this one over here took us 8. Are both of them correct? Yes. Are both of them doing the same thing? Yes. But one is half the length of the other if you remember that congruent supplements theorem. So 5 and 8 are supplementary. I'm going to circle those, 5 and 8. We want to prove that A is parallel to B. So again, we can't use if parallel anywhere in here. 5 and 8 are supplementary, that's given. 7 and 8 are supplementary. There is our linear pair postulate. And this has taken that short track. So if 5 and 8 are supplementary, 7 and 8 are supplementary, then what that congruent supplements theorem tells us is that 5 and 7 are congruent. So congruent supplements theorem. And then A is parallel to B because if I look at 5 and 7, they are corresponding angles. And if corresponding angles are congruent, then my lines are parallel. So the distance from a point to a line is always going to be perpendicular to that line. Let's see, perpendicular. So it's going to be the perpendicular distance from the point to the line. That'll be the shortest distance possible. We're just going to run through a few little theorems here. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. You might actually use that in a couple of proofs. So you could just put if linear pair congruent, then lines perpendicular, something like that. If angle 1 is congruent to angle 2, then G is perpendicular to H. If two lines are perpendicular, they intersect to form 4 right angles. And these would all be 90 degrees or right angles, interchangeable. If you are given that angle 1 is congruent to angle 2, what could you conclude about lines A and B? Well, they form a linear pair, so these have got to be perpendicular to one another. If two sides of two adjacent acute angles are perpendicular, then our angles are complementary. So if BA is perpendicular to BC, then 1 and 2 are complements. Okay, I'm going to skip over this proof because we don't really need it and you'll get plenty of practice, so we're going to bypass that one for now. If a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. Now let's talk about this. The minute that we see two parallel lines, we know that these are already coplanar, because any two parallel lines are always coplanar. So if H is parallel to K and J is perpendicular to H, then J is also perpendicular to K. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Notice this, in a plane. Okay, so they must be coplanar in order for this to happen. If M is perpendicular to P and so is N, then M and N are parallel to each other. The reason that the in a plane matters is one of these could be tilted just a little bit and still be perpendicular. You could also have, we discussed this, I think at the beginning of this unit, if you have a box and let's say everything here is right angles, then if this is A, B, and C, technically B is perpendicular to both A and C, but A and C are not parallel to each other. Okay? Is C parallel to D? In this case, yes, because they all lie in the same plane and they are both perpendicular to line A. And is B perpendicular to D? The answer to that is yes, because if C and D are parallel and B is perpendicular to C and they all lie in the same plane, then B is also perpendicular to D. You don't have to write all of that out. I just want you to kind of think through that process. And then let's discuss the difference between exact and approximate. So we kind of touched on this at the beginning of Unit 1. An exact answer, I'm going to write this down. An exact answer might be something like 5. Done. You didn't have to round it. It could be a terminating decimal, like 0.5, that is the same thing as 1/2. Or it could be a radical, like 2 square root 3. All of these are exact answers. The minute that you round something, it is no longer exact. So if we want to talk about distance, I'm going to use Pythagorean theorem here. I have 1/3 to find the distance. So if I do 1 squared plus 3 squared is equal to c squared, this is 1 plus 9. So 10 is equal to c squared, and then take the square root of both sides to give us the value of c. Now, this square root of 10 will be our exact answer. And if you plug that into the calculator, you will end up with 3 point something. Let me plug this in here. So here is exact, and our approximate would be 3.16 that is rounded. So anytime we round something, we have taken it out of exact form. If you have a terminating decimal, then it is okay. That is an exact answer. But just kind of as a rule of thumb, do not round unless you are specifically told to do so. Just as a good rule of thumb, whether you are taking one of the quizzes or tests, particularly as you move forward in mathematics, exact answers are going to be very important at those higher levels.